Okay, so picture this for a second. You are staring at a massive mountain of unstructured data. I'm talking millions of scattered documents, emails, research papers, just piled up to the ceiling. Organizing all of that manually? Yeah, right. It's an impossible challenge. But what if I told you that we now have the technology to make sense of this chaos entirely automatically? Welcome to our explainer on text clustering and topic modeling. Today we're focusing on how artificial intelligence can take massive text datasets and organize them natively, finding hidden structures and real meaning without needing any constant human handholding or, pre-existing labels. To make this super concrete, we're going to explore a really fascinating question. How exactly does an AI read and organize tens of thousands of documents without any human labels to guide it? For our core example today, we're diving into a dataset of 44,949 archive research papers. These are all focused on computation and language, and they span over 3 decades of research, from 1991 all the way up to 2024. Basically, we are going to watch the machine organize 30 years of complex science, completely on its own. Okay, let's dive into this. First, the power of text clustering. Second, the 3-step clustering pipeline. Third, visualizing the clusters. Fourth, leveling up, topic modeling. And fifth, BERTopic, building with Legos.
Section 1. The power of text clustering.
Now, in the industry right now, supervised learning techniques like classification, where humans have to painstakingly label all the training data, have pretty much reigned supreme. But the raw, unsupervised potential of text clustering is incredibly powerful. Honestly, it's really understated. It allows for these highly creative solutions that just aren't bound by human supervision. Let's look at the absolute fundamentals here. Text clustering essentially takes a messy pile of input documents and groups them into a neat output based purely on their semantic meaning. So, if the AI reads a document about cats, it naturally places it near documents about dogs. A document about soccer, that goes near basketball. And it's not just matching exact words. Modern language models genuinely understand that soccer and basketball share the overarching abstract concept of sports.
Section 2. The 3-step clustering pipeline.
So how do we actually pull this off? Well, we are going to follow the journey of a single document as it travels through a standard algorithmic pipeline. Because no matter what advanced tools you're using, a highly effective text clustering pipeline almost always boils down to 3 core steps. Step 1, convert the documents to embeddings. Step 2, reduce their dimensionality. And step 3, cluster those documents. Let's walk through these one by one.
Step 1 is embedding. The thing is, AI doesn't read English, it reads math. So we have to convert our text into numerical representations, which we call embeddings. These numbers are specifically designed to capture the deep semantic meaning of the text. For our archive dataset, we run the text through a really powerful, lightweight model called 10helpers/GTE small. And for every single document, this model spits out an embedding with 384 dimensions. You can kind of think of this as the AI scoring the document on 384 different invisible characteristics. But here's the catch. 384 dimensions is mathematically huge. Finding relationships in a space that complex is incredibly tough. So we need step 2, dimensionality reduction. We have to compress this high-dimensional space into a much lower dimensional representation. To do this, we use an algorithm called UMAP. UMAP is just absolutely fantastic at squashing our 384 dimensions down to just 5 dimensions, while somehow magically preserving the global structural meaning of the data. Which brings us to step 3, clustering. Now that our data points are compressed into a much more manageable 5-dimensional space, we can finally group these points together using a cluster model. This is the exact moment where the machine decides which documents actually belong together, based entirely on how close they are to each other in this mathematical space. But the specific algorithm we choose here is absolutely critical. We're usually comparing centroid-based methods against density-based methods. Here's the key difference. Centroid-based methods, like the famous k-means algorithm, require you to tell it exactly how many clusters exist beforehand, and then it literally forces every single point into one of those clusters. But with our archive papers, we have absolutely no idea how many topics there are. That's why we use a density-based algorithm called HDB-scan. It autonomously finds dense microclusters of documents, and, crucially, it doesn't force everything into a group.
And this brilliantly illustrates exactly why HDB-scan is so superior for a task like this. Notice the gray outlier dots. In any archive of scientific research, you are absolutely going to have weird, highly niche papers that just don't fit into a broader trend. HDBaScan beautifully handles this noise by simply ignoring them and leaving them unassigned as outliers. In our dataset, this algorithm automatically discovered exactly 156 distinct semantic clusters, completely sidestepping all that messy noise.
All right, section 3, visualizing the clusters.
Okay, we've built the mathematical pipeline. Let's get to the visual payoff. It's time to actually see what the machine has built for us out of those 45,000 documents. This is the real aha moment. What you're looking at is a 2D scatterplot of 30 years of scientific literature. Every single colored blob represents one of our 156 semantic groupings. The machine figured out all on its own that those papers belong together. And all those gray dots scattered like dust in the background? Yep, those are our unassigned outliers. It's literally the structure of human knowledge mapped entirely by AI. Moving right along to section 4, leveling up with topic modeling.
Now, this map is visually stunning for sure, but we need to pivot our narrative just a little bit. We've successfully grouped items together, which is clustering. But to make this truly useful, we have to level up. We need to actually give these clusters names. We need to know what they mean. This is where topic modeling comes in. If we manually inspect a cluster and realize every single document inside it is talking about translating sign language, well, topic modeling is the automated mechanism that actually slaps the overarching label sign language onto that specific cluster. It extracts the core themes.
Traditionally, these topics are mathematically represented by the keywords that best capture their meaning. The AI essentially looks at the text inside the cluster and pulls out the absolute most important words. It's this fascinating blend of classic bag of words counting, which is literally just tallying up how often words appear, combined with our brand new, highly advanced semantic clusters.
Which brings us to section 5, BERTopic, building with Legos. Now we get to the star of the show, BERTopic. BERTopic is this incredibly elegant framework that perfectly marries the clustering pipeline we just built with advanced topic keyword extraction. And to extract those keywords, BERTopic uses a secret weapon called c-TF-IDF. That stands for Class-Based Term Frequency Inverse Document Frequency. What it does is actually genius. It treats an entire cluster of documents. Actually, scratch that. It treats the whole group as if it were just one giant single document. Then it mathematically weighs the words to find what makes that specific cluster unique. It highlights the crucial words while aggressively ignoring the generic stuff like the, and, or research that appear everywhere.
Now, what's really interesting about this is seeing the actual output from our archive data. Just look at topic ID 0. The top keywords are speech, ASR, recognition, and end. Even without reading the thousands of documents inside that cluster, we instantly know topic 0 represents automatic speech recognition. What about topic 3? Translation, NMT, machine, neural. Boom, that's neuro-machine translation. The AI fully organized the science, and then it literally told us what it found.
But BERTopic's true brilliance really lies in its architecture. To quote the framework's own philosophy, you can think of this modularity as building with Lego blocks. Every single step we've talked about today, the embedding model, the UMAP production, the HDP-scan clustering, they are all completely modular. If a massive breakthrough in AI embedding models happens tomorrow, you just pop out the old Lego block and snap the new one right into your BERTopic pipeline. It is entirely future-proof.
And because of this Lego block adaptability, BERTopic unlocks some seriously incredible advanced capabilities. You can do guided topic modeling to kind of nudge the AI in a certain direction. You can do dynamic topic modeling to see how topics evolve over time, which is absolutely perfect for our 30 years of data. You can do hierarchical topic modeling, zero-shot modeling, or even multimodal modeling, where you cluster images right alongside text. It is basically a highly adaptable, one-stop shop for AI language tasks. Which leaves us with one final thought to ponder today. We just watched a modular AI pipeline independently read, map, and organize 30 years of highly complex scientific research in a matter of minutes, without a single human label. So I gotta ask, what untamed data in your world is just waiting to be clustered? Thank you so much for exploring with us, and we'll see you in the next explainer.